Welcome back. In part 1, we introduced upper winds and jet streams, how they form, how they move, and why they matter for fuel and routing. Now in part 2, we'll focus on how pilots and dispatchers use real-world tools to analyze, forecast, and fly efficiently through upper-level winds. Let's begin with the FD winds aloft forecasts. These are the go-to resources for seeing wind direction, speed, and temperature at different altitudes. They're issued every 6 hours and provide data for altitudes from 3,000 up to 39,000 feet. Each forecast point shows wind direction in true degrees, speed in knots, and temperature in Celsius. For example, 730,251 means wind from 230 degrees at 102 knots, temperature minus 51 degrees Celsius. Once you learn to decode them, they become second nature in your planning. These forecasts are critical for picking optimal cruise altitudes, estimating ground speed and fuel burn, planning alternates and top-of-descent points. They also help spot wind shear zones or areas of potential CAT. Now let's talk about significant weather charts, or SIGWX. These upper-level charts highlight jet stream positions, turbulence, icing zones, and CB activity. They're essential for international and high-altitude flight planning. SIGWX charts are issued by the World Area Forecast Centers, WAFC, and are used by dispatchers and pilots alike. Jet stream cores are marked with arrows and wind speeds, and turbulence zones are labeled by intensity and flight level. These charts are especially useful over oceanic routes where radar coverage is limited. Knowing where the jet stream curves or CAT zones are located allows for safer, smoother route selection even mid-flight. Dispatch teams often combine FD winds, SIGWX, and real-time aircraft data to generate automated routing suggestions. Airlines use software that evaluates fuel savings, turbulence risk, and time savings, then uploads optimized routes directly to the aircraft. Pilots review this data via ACARS, FMS updates, or printed flight plans. You'll often see alternate cruise levels or lateral offsets designed to avoid headwinds or turbulence, depending on current upper wind forecasts. For general aviation, you can use tools like windy.com for upper wind overlays, NOAA Aviation Weather Center, SkyVector for wind barbs at selected altitudes, ForeFlight for subscribers, with route optimization features. Let's walk through a real scenario. You're flying from Los Angeles to Chicago. At FL 360, headwinds are forecast at 130 knots. By flying at FL 400, the wind drops to 80 knots. That 50-knot difference could save you 20 minutes and significant fuel. Always compare options. Sometimes a higher altitude means a stronger headwind. Other times, climbing gets you above the worst of the jet. Use the data to balance time versus efficiency, and don't forget aircraft performance limits at high levels. Speaking of performance, don't exceed your aircraft's optimum cruise level just to escape wind. If your aircraft isn't designed for FL 410 cruise, you may use more fuel or reduce safety margins. Always use the aircraft's flight manual for guidance. Now let's explore tropopause height. The tropopause is the boundary between the troposphere and stratosphere. Jet streams often flow along it, and it's where turbulence and temperature shifts can be dramatic. The height of the tropopause varies. Around FL 360 or FL 400 near the equator. Around FL 300, FL 350 near the poles. It also shifts with seasons, higher in summer, lower in winter. Modern avionics can display the tropopause level or alert pilots when nearing it. This helps avoid crossing into unstable layers or entering CAT-prone zones during long-haul flights. Let's talk about route planning with upper winds. Airlines frequently use North Atlantic tracks, NATs, or packets in the Pacific, which are optimized based on jet stream location. These tracks are updated daily and take advantage of wind flow. General aviation pilots may not fly at those altitudes, but wind data still matters. At 9,000 or 12,000 feet, upper winds can vary by 30 to 40 knots between altitudes. Flying 1,000 feet lower might mean a smoother, faster leg. Another helpful concept: wind component tables. These tools show how much of a given wind affects your course as a headwind, tailwind, or crosswind. Great for planning heading corrections and ETE, estimated time en route. Combine this with true airspeed, TAS, and you get a solid ground speed estimate essential for fuel planning and on-time arrival. Most EFBs and GPS units calculate this automatically now, but it's good to know the manual method. Let's now address altitude changes in flight. If turbulence increases or wind shifts unfavorably, requesting a new cruise level is standard procedure. You'll often hear request climb to FL 380 for smoother ride and favorable wind. ATC generally accommodates these requests when traffic permits. Use PREPs and ACARS messages to share conditions with other pilots. The more info shared, the better for everyone on the route. Speaking of PIREPs, these are crucial at upper levels. Reports of light chop FL 370 or moderate turbulence FL 390 help guide others to safer air. PREPs often include wind speed and direction, giving real-world confirmation of forecasts. Let's look at automatic turbulence reports. Some airliners are equipped with sensors that measure turbulence via accelerometers. This data is sent anonymously to forecast centers, improving accuracy of CAT zones and wind models. Another helpful tool is the EDR, eddy dissipation rate. It measures how quickly turbulent energy spreads. EDR-based turbulence forecasts are highly detailed and are used in both commercial ops and advanced flight planning systems. Before we wrap up, remember that upper wind knowledge equals efficiency and safety. A well-informed flight plan accounts for tailwind opportunities, turbulence zones, fuel flow estimates, real-time weather changes en route. Let's recap Part 2. Use FD winds and SIGWX charts to understand upper-level flow. Combine with PIREPs and EDR data for turbulence avoidance. Plan cruise altitudes for wind advantage and smooth air. Adjust in flight as needed, using onboard tools and ATC coordination. Communicate good wind data benefits every aircraft in the sky. In the next episode, we descend from the winds and return to water in the form of clouds and precipitation. We'll break down how clouds form, what they mean, and how to interpret them from both the air and the chart. See you in Meteorology number 27, Clouds and Precipitation, Part 1.